Okay, so as you can see, this is our chapter 4, and start from this chapter, we move the topic from the hydrostatic to kinematic. Okay, so most of the topic involved in the following slide are related to the kinematic problems. So the title is the Bernoulli equations and the pressure variance. Okay, so the slide just shows some key concept for this chapter. As I mentioned, we are focused on the kinematic. So there are kinematic properties such as the motions, velocity, acceleration are required to solving the problems. And we need to try to use a mathematic descriptions to describe the flow condition and the flow field. And how the methods we can describe the flow conditions. So we will introduce the straight line, path line, and the track line to visualize the flow field. And what kind of the flow condition I will teach in this chapter. As you can see, we put some important flow conditions. You can see the steady flow, uniform flow, laminar flow, turbulent flow, and the inviscid flow. So all the flow conditions I will introduce later. So that's a very quick concept we will teach in the following class. And the slide just summarizes all learning outcomes for each subtitles. So the first, we wondering to describe the flow field. So I will explain what's the straight lines, what is the track line and the path line. And we have the two approach, Eulerian and the Lagrange approach, to describe the motions of the fluid particle. Okay? And then we move to the topic related to the kinematic properties. So I will teach you how can we calculate the velocity and what is the velocity field and how can we define the fluid particle acceleration. Okay? And there are two important equations we'll teach in this chapter. The first one is Euler's equations. And the second one, we call that the Bernoulli equations. We are showing the title chapter. Okay? So right now, you didn't know what the meanings for the Bernoulli equations. But in the following subtitle, I will apply the Bernoulli equation to do the velocity and the pressure measurement. Okay? So the idea is the Bernoulli equation can help us to determine the velocity and the pressures along the straight line at the different point. And what are the device we will use? We will use the piezometers and the stagnation tube and the pitot static tube. We will apply to measure the pressure. And then we can compute the velocity in the field, in the flow field. And the final chapters, we will apply above equations, but we change the flow to the irrotational flow. Okay? So because the flow, sometimes we will define the flow is rotational or non-rotational. So we will have the different concept based on the different flow conditions. But the topic we want to compute is the velocity and the pressures. Okay? So the first, we should teach you how can we describe the flow field. Okay? Because we see the flow, and how can we determine the flow field. So the most important 3 lines I'll show it on the slide is the string line. So what is the string line? You see the sentence definition here. The string line, that is a tangent. Important words is a tangent everywhere to the local velocity factor. Okay? After you read in the sentence, but you may not really understand what are the meanings. So in the following slide, I will teach you how can we see the string line. But another important is the mathematical representation for the string line. It's just based on these equations. So you see the idea for this equation is the spatial gradient will equal to the velocity gradient. So the spatial gradient, I guess you can understand. But what's the velocity gradient? So the v is the velocity along the y directions. And the u is the flow velocity along the x directions. So that's why I say the ratios for the spatial and the ratios for the velocity, they are equal for the string line. And later I will prove these equations. So you just keep in mind for this equation. The equation can help us to determine the string line functions. And we can plot the string line. Okay? So it's just based on these equations. And the straight line is the line generated by the tracer fluid. Okay? Such as the dye and continuously inject into the flow field at the starting point. Okay? So later we have some smokings, and you can check the smoking at a different time, and you will see the smoking tracer will randomly distribute around the air conditions. And the final is the path line. The path line is a fluid particle just moves through a flow field. So the path line is really just quite easy understand. The path is just track the particle at a different time, and the line is the path line. Okay, so maybe you're still confused. So this slide just summarize how can we draw the path line and how can we draw the track line by yourself. Okay, so we first need to understand what's the conditions. So you see the string line for the time point less than t0, and the string line, the direction is go to the right. Okay, this is going to the right. But when the time point is larger than t0, and we change the string line direction to the top. Okay, so you understand the string line changes with the time changes. So in that case, we will call that is unsteady flow because the string line change at a different time point. So the flow is unsteady. Okay, that means the physical properties will change when the time difference. Okay, so it's unsteady. Okay, so but right now our target is we see the path line for the time point at the t0, and the path line is like the dot showing here. This is our path line. Why? Because the string line is go to the right. So at the time point t0, before that, the particle will move to the right, right? So that's the string line initially at the t0 point is the red line. Okay? But if we change the time is larger than t0, that means the path should go to the up. Okay? Because the string line changes the direction to the up. So finally, what's your path line? The path line is first go to the right and finally going up. and then finally it's going up. So the red line showing here is our path line. So what's the path line? The path line just connection all the particle fluid at the different time. So this is the path line. Okay? So how different for the track line? Again, you can see the initially for the time point at the T0, the black solid line here is our track line. But when we change the time larger than T0, and then finally the track line changed to a different compared to the path line. So you can actually to see they are the difference if you compare the path line and the track line. The reason why, because the track line just connection all the fluid particle passing through at the same starting point. And you just connect all the fluid particle at the current time. So for the bottom, the track line is the current. At the current time, so they connect all the fluid particle passing through the same starting point and to be the track line. So this is for the current time, the point for the current time. So we know that the smoking initially at this time they stay there, but maybe 10 seconds later the smoking air will move to different positions. So the track line just connection all the fluid particle passing through at the same starting point at the current time. But the path line just connect all the fluid particle at the different time. Okay, so you can actually to see the difference between the path line and the track line. Okay, so this is a very good example if you're trying to figure out how different they are between the path line and track line. You can base on this slide. Okay, so right now I wondering to discuss with you about the how can I say the steady and how can I say the unsteady. Okay, so as you can see above slides, we are under unsteady flow. That means the physical property will change with the time, such as we see the straight line will change the directions. So that's the unsteady flow. So for the unsteady flow, we actually know the straight line and the track line, path line look different. Okay? Because the previous slide, we are under the unsteady flow. So you see a straight line and the path line and the track line are different. That means if we consider our flow is steady, and then we can say that the path line, track line, and straight line look the same, so long as they all pass through the same point, and you can say that are the same. They are the same. Okay, so that's the idea. If the steady flow, all the straight lines, path line, and the track line, they are looks the same. But unsteady, they are different. Okay, and what is the steady? I say that because you see the steady, the mathematical representation here, the velocity didn't change with the time, so the gradient is 0. So we call that the flow is steady flow. In other words, we can say that the discharge, the Q is discharge. In the following class, I will teach you what is discharge. But you can try to figure out what the steady. Steady condition indicates the physical properties didn't change with the time, and we call that the steady. Okay, so the the two figures just a very famous condition for the example show how can we draw a straight line. So you see the blue line here is our straight line, okay? And then you can say that the straight line looks are always parallel each other, okay? You can see the straight line, okay? This is our straight line here, and another straight line here, and all of them are parallel together each other, right? Okay, and what is the straight line? The straight line is we can make at a different point, we can make the tangent velocity local factors, and in that point we can make the tangent line is our local velocity factors. So that's the straight line just based on the tangent line for all of the local velocity factor, and you connect all the local velocity factors, and the line we call that the straight line. Okay, so on the right hand side, I wondering to emphasize the important point. We always call that the stagnation point. As you can see, in that point, there should be no velocity, right? Because it's just a stop there. So that's why we call that the stagnation point. So in the following, our major concept in this chapter, we wondering to understand the point along the straight line. The point along the straight line, how large the velocity here. So we need to know the flow velocity and how the magnitude for the pressure. So along the straight line, there are different points, and how change it is, how change for the flow velocity and the pressure. Can you answer the questions just based on the material teach in these chapters? So our main topic is how can we say the pressure and how can we describe the flow velocity and how large it is at any point along the straight line. This is this chapter target. Okay, so I will tell you how can we describe the flow. Okay, and then how can we draw the straight line. So before we draw a straight line, we wondering define the velocity field first. And how can I say the velocity? And what is the velocity field we have? Okay? As you can see, the velocity gives the speed and the directions of the travel fluid point at a different time. Okay? So we have the scalar is the speed, and we have the factors controlled by the directions. Okay, so the velocity is the factor. Okay, and what is the velocity field? The velocity field is a description of the velocity of each fluid particle in a flow. Okay, so that means the left hand side we show the arrow. The arrow is indicate the different velocity factor with the speed and the directions. So that figure just show how can we describe the velocity. And the right figure, we plot all the velocity factors along the straight line. Okay, and then we move to another point here, and we can draw the different arrow at the different point. So the right-hand side, we describe all the velocity factors at the different fluid locations, and then we call that is a velocity field. So the velocity field, we should have the coordinate. Because the coordinate, we know that where the location with the different velocity speed. Okay? And then at a different time, at the same point, may also have the different velocity. Okay, so the next slide, we just write down the mathematical representation form. As you can see, the velocity initially is the vector, okay? So we will have the velocity field vectors. And we have the coordinate for the x,y,z coordinates. And we have the different time, have a different velocity. And we have the unit vectors. So the unit vector will control different components of the velocity. So normally we use the U. It indicates the velocity along the x. And we use the V is the velocity along the y. And we use the W is the velocity along the z directions. Okay, that's why we put the different symbol. Here is U, V, and W. We for the I and the J and the K unit vectors. Okay, but sometimes this is only for the maybe it's convenient to describe the linear flow. But if we can see the bottom, the flow is the curve. The straight line is the curved straight line. So the bottom is the curved straight line. When we consider the curved straight line, we will move the different coordinates. And then we change the coordinate to represent the velocity field. We use the tangents. So this is the tangent directions. And this direction is our normal directions. Okay? So sometimes it just depends on your straight line shape. If the straight line is a linear straight line, you will say that I can use the x,y,z to understand the velocity field. But if you change it to the curvature straight line, you may change the component to the tangent and the normal directions. Okay? So that's some ideas if we wondering to describe the flow velocity field. We can use the formula shown on the slide. Okay? So that's a very good exercise. How can we define the dimensional of the velocity field and what are the velocity field we have? Okay? This is a very important. Maybe we'll in our quiz, maybe we will also have a similar exercise. And you need to understand and identify by yourself what the velocity field you have. So we go back to see the equation. We have the velocity vector, okay? And we actually know we only have the one component, right? The component only have the I component. So can we determine the flow is 1D or 2D? Because you can see we have the 1D and there is the 2D. So what are the meanings for the 1D and the 2D? If we see we only have the I components, that means the velocity is 1D, right? No matter the function here is x and the y involved. So first, I will pick out the two solutions. Possible solution is I'm very sure the velocity field is the 1D velocity because I only have the I component. Okay? And I know that the 1D velocity is along the x directions. So I will pick up this answer because it's a 1D velocity field, but along the x directions. Okay? So sometimes you will confusing, maybe this is the 2D, right? Because you see you have the x and the y parameters, but it is not correct. Because you only need to identify the component you have. And we only have the component is I directions. So we only have the velocity along the x. So how the difference for the 3 times x plus the 2y is control the speed. How large speed we have, right? As you can see, I draw the flow velocity field on the right hand side here. And you can see when the x increase, the length will also increase. That's because the 3 times x and the 2 times y control how large the speed we have in the field, not correlate to the dimensional. Okay, so and another things I wanted to emphasize, as you can see along the velocity field, there is no time variable, right? There is no time variable. So that means the velocity field didn't change with a different time point, right? So also we can, based on this, we can say no, we don't have a time variable. So we can say that is a steady flow. So if we wanting to provide the same a certain flow conditions, I will say that the flow field is 1D steady flow along x directions. I will say that the steady 1D flow along the x directions. Okay, so we can identify is steady or unsteady. If the velocity will change with the time, we call that is unsteady, right? But you cannot see any time involved in the velocity field. So we call that is a steady flow. Okay, so it's just the basic idea. And right now, if we know that the flow velocity field, how can we determine the straight line function? Okay, so it's a very important idea. We call that the stream function. The stream function can help us to identify the function to plot the straight line. So we should determine the stream function first, and then we can draw the straight line based on the stream functions. Okay, so for my questions, my exercise, I given the 2-dimensional field, 2D velocity field. That indicate my velocity field will controlled by the UI plus the Vj, right? Because I'm consider my velocity field is the 2-dimensional. And I define the stream function is the per c. As you can see, this is our stream function. We call that the per c. And the per c is the function as the x and y and t. Okay? So that means the per c function will change with a different location and a different time point. Okay? And for the 2D incompressible flow, so we have the condition incompressible flow. What is incompressible? As I mentioned, the density didn't change, right? Because incompressible, so I can change the density because I cannot change the volumes. Okay? So incompressible sometimes is a condition for, we call that the fluid cannot compress. So the density didn't change. And in that way, we define the 2 parameter, the u velocity along the x direction is equal to the differential per c with the y. And we define the v velocity is equal to the minus differential per c with the x. Okay, that's our definitions. And our purpose is we wondering to figure out how large the per c we have. And can we determine the per c functions? If we determine the per c functions, we will know how to draw the straight line. So our purpose is to draw the straight line. Okay, we wondering to draw the straight line based on the per c function. And the very important equations I will teach in the chapter 5. We call that the continuity equation. Continuity equations. And if you don't understand what the continuity equation is not no matters because we will teach in the chapter 5. But we actually know the continuity equation is the differential, the density differential with the time, and plus we have the gradient, we have the spatial gradient, right? And the dot with the density multiply the velocity field factors, result is equal to the 0. This is the continuity equation, okay? And I will teach you in the following class, especially in the chapter 5. And as you can see, first we consider the flow is steady flow. So that means the physical property did not change with the different time point. So we can cancel out the one item is this one. Because the density didn't change with the time, we assume the flow is a steady flow. Okay, we cancel that because we assume it is a steady flow. So the equation we can rewrite to be the spatial gradient dot with the density multiply the velocity factor equal 0. Okay, and the second we consider our flow is incompressible flow. That means the density didn't change if you change the locations. Okay, so we can take the density outside, right? We can take the density outside because the density did not change with the location changes. So we can rewrite the equation. Just the density take outside, and the inside we only have the spatial gradient dot with the velocity factor, and it will also equal to the 0. So when I take the density outside, that's just based on the compressible flow assumption. So I take the density outside because the density didn't change with the spatial locations. Okay, so and then finally we know that we have the gradient spatial dot with the velocity field is equal to 0. Okay, and then we expand this equation. We know that it will equal to a log u and the log x plus the log v and the log y will equal to a 0. Okay, and then we put the two equations. We put the equation here and the u and v here. Okay, so we can rewrite the function to be the log and the log y. Sorry, I may take the log and the log x outside, and the inside is the u. U is the log per c and the log y plus the log and the log y, and I put the v inside here, and it's minus log per c and the log x. And you can identify that it's satisfied always 0, right? Because they are the same. You can see the final formula is here. So the perceived function is always satisfy the continuity equation because they are always equal to 0. They are always equal to 0. So the slide, I wanted to emphasize the condition. The string functions always satisfy the continuity equation. Okay, the string function always satisfy the continuity equation. Okay, if you cannot understand what I mean on the slide, but the main idea, we wanting to know the perceived function. Perceived function is our string function. If we know the perceived function, we can draw the string line. Okay, so wanting to draw the string line is our final purpose. Okay, so we know that the perceived function always satisfies the continuity equation. And the second, we know that the idea for the string line. The string line, they are always, I always emphasize, they are always the tangent to the local velocity factor. Always tangent to the local velocity factor. So that means the velocity vector, if you do the cross product with the small distance change it, but when we distance change it, and the changed direction should be parallel to the velocity vector, right? Okay, that means if we do the cross product, they are always equal to 0. Because the position change directions is always parallel to the velocity vector. Because the straight line is the vector for the tangent to the local velocity. Okay, if you base on this idea, so you can do the product operators, and you see you have the I, J, K, and you put the velocity field only have the UV, because we only consider the two-dimensional velocity. And what's the location change is a little bit location changes, so we will have the dx and dy. So you only have the k component for the cross product. So you can know that the u dy minus the v dx will equal to 0. Okay, because the cross product, the result is always equal to the 0. So you can reorganize the equation. You can rewrite to be the u divided the v will equal to the dx dy. So do you remember I have shown you the equation similar before, and we call that is the spatial gradient will equal to the velocity gradient. So that's the straight line definitions. The straight line always satisfies these equations. The spatial gradient is equal to the velocity gradient. And you can also rewrite the equation to be the dx over u and the dy over v. Okay, it's the same. It's the same idea. So how can we determine the straight line? If we have the u velocity and the v velocity, based on this equation, we can do integration to see what's the function we have. Okay? So you may still confusing. So in the following, we have the exercise, and you can see how can we do the straight line. How can we draw a straight line? Okay, so we go back to see. Right now we have the equation u dx dy minus the v dx will equal to 0. Okay, and as I defined before, the u will equal to the perceived differential dy, right? And the v will equal to the minus perceived dx. Okay, this is our previous definitions, and we put the uv in this inside this equation. So we have the perceived dy multiplied dy minus we have the minus here, and we have the minus here. So here will be the positive, and the perceived dx multiplied dx. Okay, and then you will see that will equal to the 2 times perceived, right? Will equal to the 2 times differential the perceived. And we actually know the 2 times the perceived will equal 0. So only one possible is the perceived is always the constant, right? Because the constant value, there is no changes. The perceived cannot change it. So that's why finally we know that the perceived function is a string function is equal to the constant values. So for Earth, we can define up to an arbitrary constant. So any arbitrary constant we can put on the perceived function. And if we put the different constant value, the string line will change. So that the perceived string function is the perceived equal to different constant value, the string line will change at the different location. Okay, So if we still confusing, but the idea is now we know that the per se finally will equal to constant values. And the different constant value will draw the different straight line. Okay, so what are the meanings? So we have a very quick exercise shown below. So that's just what I tell you the u and the v functions. And how can you determine the string function? So this is our unknown parameters, and how can we determine? So we know that certainly the v plus factor will equal to the 2x, and this is the I component, minus the 2y, this is for the j component. So based on this velocity field, we know that the u is equal to the 2x, right? And the v is equal to the minus 2y, okay? And what the s is just a dimensional unit, is the second over 1. 1 over second, okay? So if you remember, I tell you the straight line, the mathematical representation is the spatial gradient always equal to the velocity gradient. So if we still remember the equation, we can write the u divided the v is always equal to the dx dy, right? As I say, the velocity gradient is always equal to the spatial gradient. Okay? And we can rewrite the equation to be the dx u will equal to the dy and the v, right? So we can put the u and the v inside the equations. So you can still rewrite the equation to be the dx and the 2 times x is a u velocity will equal to the dy and the minus 2y. Okay? And you can see if I can do the integrations and what's happened. Okay? So I do the integrations both sides. And we will have the additional constant value, right? Because we are doing the integrations. So we can cancel out the 2 because both sides we have the 2 factors. And so if you do the integration, you know that the left hand side is equal to the ln x, right? As we remember, if you differential with the ln will equal to the x over 1. So we do the integration to be the ln x. And the right hand side to be the ln y. And we still have the constant value c, right? And then we put the log together. So we have a ln x plus the ln y will equal to the constant value. And because the ln plus together is equal to the ln multiply the inside factors. Okay? So we can rewrite it's equal to the ln xy will equal to the constant value. So finally, I can say that the xy will equal to the exponential c constant value. And the x multiply y is always equal to a constant, right? Okay? So what is your per se functions? If you base on these equations, you will say that the xy is our per se function and as function of the x and y, right? And that will always equal to the constant. And these constant values you can choose by yourself because it is arbitrary, right? Any constant value you can put, and based on these constant values, you can draw the individually straight line by yourself because you have already string functions. And you can plot the string line by yourself. So how can we draw the string line based on the string function here? Okay, So you see the next slide, if we have the velocity field, so we can plot the different local velocity factors based on the function defined here, right? And you see that the arrow length is changed with the different location because you have the x function here and you have the y function here. So you can change the speed of the velocity, okay? And what's the straight line? Because we know that the stream function is equal to the xy, and you can put the constant values. So how can we draw a straight line? For example, if xy, we know that the per C1 is equal to 1, okay? So how can we draw a line? Because we know that the point, if I put the x is 1, and the y will be the 1, okay? If I put the x to the 2, and the y will to be the 0.5, right? So you can change the different location, and maybe there is the 1 and 1, and there is the 2 and the 0.2, right? So you can draw these line functions because you setting this is the constant value is equal to the per C3. So you can just change the different constant value, and you can draw the different straight line based on the different constant values. So that's a reason why we should define the stream function first, and then we can based on the idea is the spatial gradient is always equal to the velocity gradient, and then we can find out what the stream function. And the stream function always equal to the constant value, but then you should put the constant value you want, and then you can draw the straight line. Okay, and then for each straight line, you can say that they are parallel each others. Okay, they are parallel each others. Okay, so this is just the exercise for the 2D dimensional. So right now, I wondering to try to practice another example. This is example for the 3-dimensional. So again, how can I say the 3-dimensional? Because there is a u, v, w velocity, and with the I, j, k directions. So we call that the 3-dimensional. And we know that the u is equal to the 2x, and the v is the 2y, but the z, sorry, I need to write the w, is equal to a minus 4z, right? So, and this problem is different. I already set out the boundary condition. The boundary condition, I wondering to draw the straight line, but the straight line should be cross this point. So I have the coordinate for the point is the 1, 1, and 1. So I wondering to draw the straight line, but the straight line should be cross this point. So can you tell me what's the straight line function? Okay, so again, for this 3-dimensional problem, sometimes we will divide it into a different domain. So first, I divided it into the 2D xy plane. Okay, so I divided 2D the xy plane. So again, I know that the dx and the u will equal to the dy divided v, right? Because right now I only consider the 2D xy plane. And so you put the velocity is 2x and will equal to the dy. And right now the v velocity is 2y. And again, we do the integrations. Okay, and we have the additional constant values. And again, we cancel out the same parameters. And right now, our constant value to be maybe its label is a constant 1. So we do the integration both sides. Again, we have a long x will equal to a long y, and that's the plus the C1 constant values. And we put the long together, so we know that the long will equal to the x divided the y and equal to the C1. So we know that certainly the x divided y is equal to exponential C1, okay, constant values. But right now we have the boundary condition is this equation should be close, passing through the point. The point for the x and the y is equal to the 1 and 1. Okay, so we put the x equal 1 and the y equal 1 inside the function. We can figure out the C1 constant value will equal to the 1. So the C1 constant is equal to the 0, right? So what's our final stream function for the xy plane? We know that the result, the answer finally is x divided 1 always equal to 1. And then we know that the x is equal y, is equal to y, right? So if we consider a 2D plane at the xy, and we can say that the x will equal to y. This is our stream function located at the xy 2D plane. So the second, I wondering to move to a different plane. So right now I for the 2D plane, but right now I can change to the xz plane, okay? And how can we solve these problems? Again, we actually know the dx and the u will equal to the dz and the w velocity, right? Okay, so we can put the velocity inside the problem. So the u 2x, and the right hand side we have the dz, but the omega right now is minus 4z. Okay, so again we can cancel out the 2, and then right now we have the 2 times in here, and we do the integrations both sides, and we have the another constant value C2. So we can say that this is long x, and the right is minus 2 over 1, and the long z and plus the C2. So both sides we can multiply the twice times. So now we have the 2 times long x, and there's a minus long z, and we keep the constant is still a C2. Okay, it's just a constant, so I didn't change the label. And we move to the long, move to the left, so it's to be the plus. So we merge the long together is 2 times, because I put the power inside the x to be the x squared, and multiply the z will equal to the C2. So finally we know that the x squared, the z multiplied d will equal to exponential C2 powers. So what are our conditions? The boundary condition right now is the x and the z is also equal 1 and 1. So we put the number inside, finally we still can say that the C2 also equal the 0. So we can conclude that the x squared multiplied d will equal to 1. Okay, so the z will equal to the x squared and 1 over x squared. Okay, so that's our another answers. For that, the main idea is no matter the flow field is 3-dimensional or 2-dimensional. You just keep in mind the idea is the spatial gradient always equal to velocity gradient. So you just based on this idea, and you have the velocity function. If you don't have the velocity field, you can't find out the string function. If you don't have the velocity field, you cannot find out the string function. If you don't have the string function, you cannot describe the string line. You cannot plot the string line. So you cannot understand the velocity field. Okay? So that's the two important things. First, you should know the velocity field. And the second, based on the velocity gradient, will equal to the spatial gradient idea, you can find out the string function. You have the string function, so you can draw the string line. Okay? So it's very important today. We should keep in mind. So the following slides, I wondering to move to the different part. I wondering to teach you the two approach to describe the motion of the fluid particle. So as I mentioned, we have the Lagrange and the Eulerian approaches. So what's the Lagrange? The Lagrange, you can see we need the initial point. So this is our initial point, locations at the time 0, okay? So for the Lagrange, we should know the initial point locations, and then we should know the velocity as function of the time. So there is no spatial variable. We only need to know the velocity change with the time functions. And then we can predict. So we're wondering predict the new location. Okay? So that means if we have the velocity and I have the initial point, so I can predict the new location for different time points. So at the time t1. So no matter when the time we have, but we just based on this idea, so I can predict the new positions. So this is for the Lagrange. So for Lagrange, we should based on the initial point. It's very important. So if you don't fix the one point, you cannot check the point at a different time. So the initial point is very important. But what the Eulerian? As you can see, the Eulerian is to be, the property is to be the evaluate at the spatial location. Spatial, so the different, we need the spatial location. As a function of the time, because the Eulerian is based on the field concept. So sometimes we say the Eulerian methods, we call that is the field concept. So compared to the Lagrange, there is no spatial variable. But the Eulerian, we should have some parameter properties as a function of the spatial. Okay? So sometimes we always confusing. So we can have some exercise, you can understand how different they are. So this is an example for the rest and falling under the actions of gravity. Okay, so the left-hand side is the Lagrange methods, and the right-hand side is the Eulerian methods. As I mentioned, the two approaches are applied to describe the motion of the fluid particle. So how the Lagrange? The Lagrange, the first, we should pick up the initial point. So this is our initial point, okay? This is the initial point. And we have the two functions, V is equal to the GT, right? And S is the elevations is equal to the GT squared over 2. Okay, this is the basic the motion equations. So we have the motion equation, they are the time function, right? They are the time functions. So we can predict anywhere we want. For this point, I can predict the position, okay? And I can predict the velocity in that point, right? So the Lagrange, the most important thing is the initial point. And then we apply the time functions, the velocity and the location. We can predict the new locations at a different time and with the different magnitude of the velocity. But the right-hand side is the Eulerian, how different. The Eulerian directly tells us the velocity will equal to the root of the 2g elevation. The velocity will equal to the root of the 2g elevation. So you just need to figure out, okay, at these locations, and I know the elevations for this location, maybe here is the D1. So I only need to put the D1 into the equations, and I know how large it is, the velocity, right? So the Eulerian, we didn't need to know the initial point. We only need to know the location coordinate. And then we put into the functions. The function is the physical property as a function of the spatial location. So we know the location and we can predict the velocity. So we don't need to require the initial point. Okay? So sometimes the Lagrange, like the tracer, I pick out one person and I look the person. And when the person moving at a different time, I still look him. Okay? But the Eulerian, we didn't know where is the person. We just pick out one point and I can predict the person velocity. Okay? So that the idea is different. So the table just summarize all the concept between the Lagrange and the Eulerian. So I just highlight some important difference they are, and with the red square. And you can see the first, this is we need to fix the point. So the fixed point that indicate we fix the initial point. But the Eulerian didn't need. You just know the spatial location coordinate is fine. We don't fix. So that the meaning is the same. We need the initial point x0, y0, z0, and the time. And we can predict the anywhere, the new positions with the different velocity. But for the Eulerian, we don't need. We only need to know the anywhere, the coordinates of the locations. So the Lagrange is more difficult to apply in the real case. Only can apply to the closed systems. Because of Lagrange, we need to check the fluid particle. But sometimes it's very difficult to track the same fluid particle in your system. So Lagrange can only apply to the closed systems. But the Eulerian, we always apply to the control volume. And then right now you don't know what the system we call that the control volume. So in the following chapter, I will teach you. So if you don't know the certain definition for the Lagrange and the Eulerian, you can go back to see the exercise here. They are the difference, so it's easy to identify and figure out what they are different. Okay? So right now I will spend around 5 minutes to go quickly to introduce the different flow conditions as you can see on the slide. So the first one, we call that the uniform flow. So what is the uniform flow? As you can see, the velocity is constant, uniform. So the velocity is constant with the magnitude and the directions along the straight line at a different time point. That means along the same straight line, the velocity along this trend line, if there is no changes in the velocity at the different location, and then we will call that is the uniform flow. So you see the uniform flow, all the straight lines are parallel, and they are the linear straight line, not the curve straight line, and they always parallel each others. But the right hand side, we call that the non-uniform flow, as you can see for the convergent flow and the vortex flow. The vortex flow is a rotational flow, so the velocity always change because the velocity directions will change along the circle, right? And the convergent flow, you can see that the convergent finally will cross together. So also we call that is a non-uniform flow. So the idea is very simple. For the mathematical representation for the uniform flow, the velocity didn't change with the location. So the gradient is equal to the 0. Okay? So it's very easy to identify its uniform or non-uniform flow. And we will have the laminar flow and the turbulent flow. Sometimes it's very difficult to understand. So I put the one velocity profile. This is the velocity profile. As you can see, the velocity is along the x directions. Okay, so this profile velocity that indicates if I know that this is y directions and there is x directions, so the velocity will change along the y directions. But this is the velocity profile. We can see that is the parabolic, right? So that's a parabolic profile usually we use to describe the laminar flow. But if right hand side is the turbulent flow. And what you see for the velocity profile, we see this velocity profile looks similar to the uniform flow, right? The uniform flow that indicates the velocity is almost the constant values. So this looks similar to the uniform flow, but not at all. Because you can see there are some fluctuations. There are some fluctuations along the velocity profile. And these fluctuations, usually we call that the velocity perturbation. The velocity perturbations. And sometimes we also call that is the AD. Okay, this is the AD. AD is the volume. Okay. So that is a very terrible flow condition because the small velocity perturbations will disturb the flow condition. Okay, so sometimes until now we cannot find out the mathematic form to describe this turbulent flow velocity field. So usually we will calculate the average velocity and plus the velocity perturbations to describe the local velocity in the turbulent flow. Okay, so the main idea is the turbulent flow, the velocity profile like the uniform flow, but there are some velocity perturbations, and we use the U prime to represent the velocity perturbations. Okay, so until now, the Reynolds developed the number, so we call that the Reynolds number, can help us to identify is the turbulent flow or laminar flow. So we define the values here, and then we define the certain threshold. If the Reynolds number smaller than 2100, we call that the laminar flow. If the Reynolds number is larger than 4T hundreds, and we call that the turbulent flow. And this equation is for the pipe flow. And how can we compute the RE Reynolds numbers? So the rho is the density. It's your fluid density. And the U is the flow velocity in the pipe. And what's the D? D is the diameter of the pipe. And what is the mu is the dynamic. If you remember, this is the viscosity. So we have the 4 properties, and we can define how large the Reynolds number we have. And then we can describe the flow is a laminar flow or the turbulent flow, just based on these values. But this is an equation especially for the pipe flow. Okay, if your flow condition is not in the pipe flow, you cannot say. Okay, so the final flow conditions I introduced today is the viscous flow and the inviscid flow. So sometimes the problem we meet, we always assume the flow is inviscid flow. So that means for the inviscid flow, because there is no viscosity effect. No viscosity effect, that means no shear stress involved in our problem. Okay, so today I did very quickly, but some flow conditions we can remember is steady, unsteady, uniform, non-uniform, laminar flow, turbulent flow, incompressible flow, viscous flow, inviscid flow. That's all. So all the flow conditions I mentioned will happen in our following class. So you need to know the certain definition for the flow condition. Okay? So we may stop here.